Think about it for a second. The fan, your fridge, the train you might have taken this morning, they all run on electric motors. I mean, these things are the invisible workhorses of our entire world. But what if I told you that for decades, most of them have been running with this staggering, just built-in inefficiency? Well, there's a simple fix that's changing absolutely everything.
Yeah, this is really the core question, isn't it? I mean, just imagine driving your car with only two options: engine off, or the pedal is slammed to the floor. Nothing in between. Sounds crazy wasteful, right? Well, believe it or not, for a long time, that's pretty much exactly how we've been running most of our electric motors.
And look, the scale here is it's mind-blowing. We are not just talking about your refrigerator. Electric motors range from a tiny fraction of a watt, think about something like a watch, all the way up to hundreds of megawatts for these enormous building-sized pumps in hydroelectric plants. They are literally the muscle of our entire industrial and domestic world.
Okay, so if these motors are the powerful muscle of our world, then what's the problem? Well, for decades, that muscle has been, let's say, incredibly unsubtle. It really all comes down to its most fundamental design.
You see, a standard AC induction motor, and that's the most common type out there by far, is built for one thing: to connect directly to the power grid and spin at one single speed. And that speed is dictated by the grid's frequency. It's a total brute force approach. It's either on, full tilt, or it's completely off. There's just no in between. It's kind of like having a simple light switch for a super powerful machine.
And this whole on and off method, well, it creates a whole cascade of problems. I mean, wasted energy is the obvious one, sure, but it goes way deeper than that. Just starting a motor this way causes a massive electrical surge. It's called an inrush current. It can actually mess with the power grid. Plus, it creates what experts call abrupt mechanical stress on everything connected to it. It's literally like revving a car to redline every single time you start it. You can just imagine the result: more wear, more maintenance, and yeah, a lot more noise.
So, to get around this all-or-nothing problem, for a long time, engineers were stuck. They faced this really difficult choice. They had to pick between two fundamentally different kinds of motors, and each one came with its own major trade-offs. It was a real classic engineering dilemma. So here was the dilemma. On one hand, you had DC motors. Now, these offered fantastic speed control, but they came with these mechanical brushes that would wear down, and that meant constant, expensive maintenance. On the other hand, you had the rugged, cheap AC induction motor. The problem? Getting it to change speeds was historically super complex and really inefficient. So the choice was painful. Do you get the control you need and just pay for it in maintenance, or do you get reliability and just sacrifice control?
But then, everything changed. Thanks to these huge advancements in power electronics, a breakthrough technology came along that completely, and I mean completely, changed the game. It finally offered the best of both worlds. You got the precise control of a DC motor, but with the rugged reliability of an AC motor.
And this is where the variable frequency drive, or VFD, comes in. Think of it as a smart power converter. It's a little box that sits between the power grid and the motor. And instead of just letting that raw, fixed frequency power from the wall slam into the motor, the VFD grabs that power and, well, it completely reshapes it. It gives the motor exactly the right kind of power it needs for any given speed.
So how does it work? Well, a VFD performs a kind of electrical alchemy, really, in three key steps. Okay, so first, a rectifier takes the incoming AC power from the grid and turns it into DC power. Second, that DC power gets smoothed out in what's called a DC link. And then third, and this is the really clever part, an inverter takes that smooth DC power and chops it up, basically, to build a brand new custom AC signal at any frequency the motor needs. You want half speed? The VFD makes a 30 Hz signal. Full speed? 60 Hz. It gives you total, precise control.
Now, the magic behind all this is a technique called pulse width modulation, or PWM. It sounds complicated, but the idea is actually pretty cool. The inverter switches on and off thousands of times per second, creating this series of rectangular pulses. And by rapidly changing the width of those pulses, making some a little longer, some a little shorter, it can perfectly simulate a smooth, brand new AC wave. The best way to think of it, it's like a master chef using tiny, super precise ingredients to create the absolute perfect power recipe for the motor, moment by moment. Okay, so we've solved the control problem. We've basically given this rugged, reliable AC motor an infinitely variable gearbox. So what does that actually mean? What are the real-world results of giving it this newfound intelligence?
Well, the single biggest reward is a massive reduction in energy use. And this is especially true for the most common applications, like pumps and fans. See, with a fixed-speed motor, you typically control the flow using a valve. That's kind of like driving your car with the accelerator floored and controlling your speed by right of the brake. It's just incredibly wasteful. But with a VFD, you just slow the motor down. It's that simple. And the energy savings are, honestly, they're often dramatic.
And here's the really wild part. The relationship isn't linear, not even close. Because of something called the affinity laws, a small reduction in speed leads to a huge reduction in power use. Get this, reducing a fan's speed by just 20% can cut its energy consumption by nearly half, almost 50%. It's an incredible relationship, and VFDs are what allow us to unlock those savings.
But listen, the benefits go way beyond just the electricity bill. VFDs give you what are called soft starts, where they gently ramp up the speed instead of slamming it on. That eliminates all that mechanical shock, which means less wear and a much longer life for the equipment. You also get super precise process control, quieter operation, and even advanced features like regenerative braking. Yeah, where the VFD acts just like the brakes in an electric car, capturing energy as the motor slows down. It's a total system upgrade.
So you see, this technology isn't just some small improvement. It's really a foundational shift in how we control the machines that run our entire world. We're literally making our industrial backbone smarter and way more efficient.
And here's maybe the best way to think about it. For about a century, the electric motor was just dumb muscle. Super strong, super reliable, but it was only capable of one action: go. The VFD is the microprocessor brain that finally gives that muscle finesse, intelligence, and real adaptability.
And this evolution has just been accelerating like crazy. We went from those simple, clunky on-off switches to the high-maintenance DC drives, then to the first practical VFDs. And today we have smart VFDs that are just packed with sensors. They connect to factory networks. They run their own self-diagnostics. They're a key piece of the fully automated factories of the future.
And really, that's the key takeaway here. This technology isn't just for giant industrial pumps anymore. It's getting smaller, it's getting cheaper, and it's becoming more and more integrated into our daily lives. We're talking HVAC systems, elevators, even some of your home appliances. So the real question now isn't if we can make our motors smarter. The question is, what can't we make more efficient? The possibilities really are just beginning.